Welcome back all of you to the virtual classes of Scientia. Here we are continuing with the concept of moment of inertia in rotation and how does it act as the analogous property of mass. And in the last session of moment of inertia and moment of inertia of a single particle, which we have done as a previous video, I have shown what is moment of inertia? Moment of inertia is defined as analogous quantity of mass in rotation, or we can call moment of inertia is that property of an object by which it opposes any change in its state of rest or motion with a uniform angular velocity unless it is acted by an external unbalanced torque. And we found what was the expression for a single particle. Now let us extend the concept into a system of particles by using the same derivation. I have done this one for a single particle, you must be remembering in the last session. I am going to extend this one into the concept of a system of particles. Say a single particle, I am changing this one into a system of particles. Moment of inertia of a system of particles. So if you have understood the single particle system, then this will be very simple for you. A system of particles. That means there is not one particle there, we have n number of particles. Say we have n number of particles to deal with. So for a single particle, what we have done over here is we considered its rotation about an axis and its tangential velocity and all we have considered. Now, and for that we have got the expression for the moment of inertia as mr squared by doing this process. Now let us assume that instead of the single particle, I am calling it as the first particle, or say ith particle. This is the first, let this be the first particle m1. It has got a distance of r1 from the center. Imagine that there is another particle m2 which is at a distance of r2. There is m3 with r3. But here is m4 with r4. Or there are n numbers over here, so that I can consider the entire system as a part of a very large body, or this is a big object, or we will call this one as a continuous distribution of masses. m1, m2, m3, m4, say m5, say m6, or maybe mn is here. There are, suppose, n number of particles are there which are revolving about the axis with omega, and there is an angular acceleration alpha. So I have got the expression for the torque for a single particle as r cross f. I call this one as r1, this one as f1. So this is tau 1 is equal to r1 cross f1. I got it as r1f as r1 and f1 were perpendiculars. Similarly for r2, if this is r2, say f2 is acting on it, I'll get, instead of this, tau 2 is equal to r2 cross f2. r3, tau 3, this is r3, tau 3 is equal to r3 cross f3. For nth number, tau n is equal to rn cross fn. Or I may generalize this one as for ith particle, say ith particle, tau I can be written as ri cross fi, or this is tau I fi. Correct? So that is my expression for ith particle, the torque experienced by the ith particle. So this will be Ri, Mi, ATI, Ri, Mi, alpha I, Ri, as Fi is equal to Mi, ATI. This is force acting on the ith particle. Force acting on the ith particle is mass into tangential acceleration. We got the expression. And the tangential acceleration for any particle ATI can be written as alpha ri. So I got this expression. So I can put 2I as mi ri square alpha I. What about alpha I? Angular acceleration of the ith particle. We consider this one as a system of particles. If this is a rigid system, what we have to expect is alpha 1, which is the angular acceleration of the first, is equal to alpha 2 is equal to alpha 3, etc. up to alpha I. Why that is required? Because if the angular acceleration of different particles are different, what will happen? Different particles will be accelerated with different angular acceleration. That means if this is a rigid body, if this has got 1 point, if that is rotating with say 3 radian per second square, if the other one is rotating with 5 radian per second square, what will happen? If one is rotating with 3 radian per second square and the other one is rotating with 5 radian per second square, after some time what will happen? The 5 will be distorted and it may be somewhere over here. If 3 is here, 5 will be here. That means the shape of the object will be lost. That means if M1 is here, M2 will move into that one. That means the body will get distorted. Then we cannot call it as a rigid body. So if this is a rigid body, or if the particle is rigid, what is to be followed? The angular acceleration of each particle have to be a constant, or we can express it as a single value alpha I, or it can be expressed as alpha. So instead of alpha I can write it as alpha. So for the ith particle, this is the expression. Why we got alpha? Because alpha values for any particle should be the same. Now, I got the torque acting on a single particle. If I want to find the torque acting on the entire system, what I have to do? I have to go for a summation. So the total torque will be equal to sum of, say, I is equal to 1 to n mi ri square multiplied with alpha. Because this is for only a single particle, we have n number of particles. So I will get the expression as sigma I 1 to n mi ri square into alpha. This is the total torque for a single, total torque for a system of particles. This is can be written as what? I into alpha for that system. So for a system of particles, what will be the expression for torque? I mean, the torque is equal to I alpha, and I is equal to sigma I 1 to n mi ri square. So that is the expression for moment of inertia of a system of particles. Moment of inertia of a system of particles. We have started with a single particle and we have considered n number of particles, and all of them are rotating about the same axis. So if the body is rigid, then alpha values for all of them should be the same. So I can write tau I is equal to mi ri square into alpha, extending into n number of particles. Take a summation, we will get sigma I 1 to n mi ri square into alpha, which is equal to I into alpha. So I for any n number of system can be expressed in this manner. So that is the expression for moment of inertia of a system of particles. Moment of inertia of a system of particles. So the general expression for moment of inertia of a system of particles can be expressed as moment of inertia. The general expression is sigma I 1 to n mi ri square for a system of, say, m1 at r1 M2 at R2, then M3 at R3, say M4 at R4, etc. Rotating with omega and alpha. So this concept helps us to understand the moment of inertia of a system of particles. And in all cases, I can express it as m into k square. M into k square. When you do some examples, you can see that this can be expressed like this, where m is the total mass of the system and k is called as the radius of gyration. Radius of gyration. So what does it indicate? See, I have expressed I is equal to sigma I1 to n mi ri square, where mi are the masses of individual particles, ri are the distance of individual particles from the axis. We can see, and I have expressed that one in a different form. I is equal to m into k square, where m is the total mass. So this is another way of looking into this structure or looking into this problem. What I mean by this one is, the same problem I can equivalently represent as an axis from which the entire mass is concentrated at an imaginary radius of k, which gives rise to the same value of moment of inertia as sigma I is equal to 1 to n mi ri square. So how we can define the radius of gyration? Radius of gyration is the distance from the axis of rotation to a particular point at which the entire mass is supposed to be concentrated. The entire mass is supposed to be concentrated, and which gives rise to the same value of moment of inertia as the original system. What is that? Suppose the entire system is giving you the moment of inertia value is equal to, say, 5 units. 5 units. And if I write, this is obtained by sigma I is equal to 1 to n mi ri square. Here I am assuming I am having an axis. I am assuming I is equal to 5 units, and this is equal to the total mass of the system into an imaginary radius square. So that is a problem. So what is the radius of gyration? It is an imaginary radius at which the entire mass of the system is supposed to be concentrated, and that gives rise to the same value of moment of inertia as the original system. So that is a way to analyze the moment of inertia of system of particles. I will do one simple example so that the concepts will be very clear to you. I will do an example of moment of inertia of a uniformly distributed ring or uniform ring. Of, say, mass m and radius r. So the problem is, I have a ring of mass m whose radius is r. What is my aim? I have to find I is equal to sigma I 1 to n mi ri square. To start with this, let us take, see, we have got it as a uniform ring. That means the mass is distributed uniformly around the circumference. So I can define one quantity that is called as linear mass density. Linear mass density, which can be expressed by lambda. What is that? Total mass divided by the total length. What is the total length? Total length is 2 pi r. So linear mass density is mass divided by 2 pi r. Okay, m divided by 2 pi r. Now let me assume there is a small elemental mass of dm which has got a small length of say dl. So what is the mass of that small element? Mass of dl. Say that is equal to dm. That will be equal to what? Linear mass density multiplied by that length. So what is the linear mass density? That is m divided by 2 pi r into dl. Ultimately what I am doing is I am converting one variable to another variable. You will see that one very soon. So there is a mass dm at a distance of r. dm at a distance of r. What will be the moment of inertia due to the small element? So I will call that one as moment of inertia due to dm. Let me call that one as a small elemental moment of inertia, that is di. We know for a single particle moment of inertia is mass of that particle multiplied by the distance. We are considering rotation about this axis. Okay. So or this is our problem. This is dm, this is the rotation, this is r. So I am taking axis through the center. This is moment of inertia for a particle through the axis through the center. Axis on the plane and through the center. Perpendicular to the plane and the center. So di, what is di? Moment of inertia due to the small elemental mass. So that mass multiplied by the distance square. So that is dm multiplied by r square. This is just similar to the first problem that we have done for a single particle. That was mr square. So substituting, I will get di is equal to dm is m divided by 2 pi r multiplied by dl into r square. So this r and r can be cancelled. This is equal to m by 2 pi r into dl. So I got the small elemental moment of inertia due to the dm. So how can I find the total moment of inertia? I have to extend this dm into the total circle, or total moment of inertia can be obtained by what? An integration through the circumference. So you can say integral of di from 0 to 2 pi r. Substituting for di, this will become 0 to 2 pi r mr divided by 2 pi dl. mr by 2 pi is a constant, so I is equal to mr divided by 2 pi. Integral of dl will give you L within limit 0 to 2 pi r. L within limit 0 to 2 pi r. Substituting the limits, this will become mr by 2 pi. 2 pi r minus 0 is nothing but that is equal to 2 pi r. 2 pi cancels. Moment of inertia of a ring is equal to mr square. So I got the expression for the moment of inertia of an object due to the uniform ring as I is equal to mr square, starting from individual discussion. So for this, as I told earlier, I can write this one is equal to what? M into k square, where k is called as the radius of gyration. So for a ring, what is radius of gyration? That is nothing but it is a radius of the ring itself when the axis is perpendicular and through the center, because the values will change when you are choosing different axes. And that aspect we will see while I am taking the perpendicular axis theorem, parallel axis theorem, and when we are going to see the different values of moment of inertia of different kind of objects. So this is just a small example so that you can understand how to get the value of moment of inertia of an object by the simple application of calculus. So thank you very much. Just go through this one again and again so that the process will be very simple to you. Thank you.